Hello and welcome to Embedded Flutter. My name is Joel Winarske, and for the next half hour we'll be covering Embedder Basics, Embedder Variants, Flutter Tooling, development workflows, a GTK Gallery Walkthrough, a Flutter-auto Gallery Walkthrough, Workspace Automation, and cover some basic testing options. Embedder Basics. The component here is the Flutter engine. It's a unique build, which is different than a desktop embedder build. So it's built targeting embedder. Desktop builds include platform-specific features not applicable to an embedded application, so they're turned off. The Flutter engine is controlled by a shell, and for AGL, we have no forks or changes as is. The engine repo is located here. So for the shell component, that covers the Flutter application lifecycle, user input, mouse, keyboard, touch, task runners, there's a general and a render, and platform channel I/O. In the case of AGL, the Embedder Shell is Flutter-auto. OpenGL and Vulkan backends are supported. Surfaces includes a base surface and a view surface, one-to-many. Each view surface has a single instance of the Flutter engine, and a view surface is capable of managing subsurfaces. OpenGL, when the backend is enabled, it enables a 2D texture registry. The user input sends Flutter engine, mouse, keyboard, touch events. Platform channel I/O and engine task runner. Flutter engine instancing. Single process is a single Dart VM instance with multiple Flutter engine instances. Typically that's one, but it can be as many as the resources are available on the device in question. In the case of multiple process, that involves a one-to-one relationship between the Dart VM and the Flutter engine instance. And that would be obviously more resource intensive. Moving on to Embedder Variants. Flutter-auto, used by AGL, is Wayland only. Supports OpenGL and Vulkan backends. It has Wayland protocol support for AGL Compositor, XDG, IDE Shell. Will be available in an upcoming open source release. Works with AGL Compositor, Weston, the GNOME Display Manager, aka GDM, WL Roots, and others. It is a multiple application instance per view. So it supports multiple views. It also supports subsurfaces. That's per view. So independently, you can have many views, and each view gets associated in a Flutter engine, and each view can have subsurfaces. So you effectively have many views that you can composite windows on. It has a JSON configuration option, which helps in configuring and setting up a multi-view scenario. MISRA compliant and a pending release. DLT logging, pending release. Sentry native CMake support, pending release. Primary focus is embedded Linux, and the repo is indicated here. the case of Flutter GTK, that is X11 and now supports Wayland. OpenGL backend is supported. It works with the GNOME Display Manager and possibly others. I have not tested very deeply on this one. Primary focus is desktop. glib paradigm, largely built by Canonical, Ubuntu. Slow to change or pick up new features. For instance, Wayland, it took a couple of years. Vulkan, etc. And that's located in the engine source tree. The Flutter engine embedder examples, they're GLFW based. A reference for some supported features of the Embedder API. One example is the damage region management. Used for regression testing, the Embedder API. And it's not intended for shipping product. And that's also located in the Flutter engine repository. Flutter Pi, this is DRM only. Supports OpenGL and Vulkan. Primary focus is IoT use cases, single display, single application, not MISRA compliant. vSync is better than the Sony DRM vSync implementation, and the repo is located here. The Tizen Sony embedders, they follow a similar pattern. Both fork Flutter SDK to implement custom tooling. Not sure if Tizen or Sony was first. The plugins are not universal Linux. It requires a custom platform definition, and all plugins of the public variety need to be forked so that you can add the flavor of the plugin. Initial goal of Sony was to get merged upstream. Doesn't look like it will ever happen. In my opinion, the proper solution, instead of forking Flutter SDK, is to implement cross-compilation in the Flutter SDK. This is something I've raised and discussed a couple times. This is simply done with a CMake toolchain file. And I have a design review planned for this year. That requires a design document, review process, and then a PR. So moving on to Flutter Tooling. In AGL, the Flutter SDK usage has no forks or patches. It is as is. IDE support for Flutter. That is Visual Studio Code, is the most popular, and JetBrains Variants. Android Studio or CLion have first-class Dart support as well. Platform-specific Linux GTK Embedder. It's built into Flutter SDK tooling. It's host only, no cross-compilation support. Custom device, that is generic device debugging, and it enables host-side debugging as well as remote debugging of Ethernet, Docker, QEMU, ADB, etc. A little more about custom devices. This mechanism is available in the Flutter SDK, and it enables debugging Flutter applications using a custom embedder. Key values are used to define the callback command sequences, and these callbacks are invoked by the Flutter tooling. If ping sees a value that matches ping success regex, then that custom device is available to use. And one way to check is run flutter doctor-v, and at the bottom it will list the available devices. Workspace Automation pre-populates custom_devices.json. That's found in the .config Flutter folder. Moving on, development workflows. I'll cover host side and device side. Listing the available devices. Here I have an example of running Flutter Doctor, and in this case I see two connected devices, and one is Linux and one is Desktop Auto. Host side, debug on Flutter GTK Embedder. So in this scenario, we want to run using the Linux GTK Embedder on our host machine. So we can log into X11 or a Wayland session, cd into My Amazing App, and execute Flutter run -d for device, and the name is Linux. As we saw in the prior slide, this second column with the bullets, there's Linux, and the one below that is desktop-auto. So that's the device name. And what this does, it builds a bundle folder, and it creates an executable in bundle folder root. When running in Wayland session, if you don't want it to default to x11/xwayland, you need to export the GTK backend environmental variable to equal Wayland prior to running. For host side, debug on Flutter-auto, log into Wayland session, source your setup environment. This happens with Workspace Automation and establishes the Flutter workspace. cd into My Amazing App and execute Flutter run -d desktop-auto. So the device Desktop Auto gets installed by Workspace Automation, and that's how that becomes available. This stages a bundle folder and runs Flutter-auto on your host machine. In the case of device side, debug on device. So device, you boot the device, a physical device, whether it's a Raspberry Pi or a BeagleBoard or you name it, physical device that connects via Ethernet or USB depending on the OS configuration. Emulator, QEMU image, or a container from a Docker image or a Docker Compose with multiple containers. And then enable debug transports as needed. So that's what we do on the device side first, and then from the host side, we source the setup environment if we have not done so already for that work session. Then cd My Amazing App, Flutter run -d remote config. So depending on the configuration that's installed at the time of running Workspace Automation, it could be a variety of devices. IDE Compatibility. So the way custom device works with the IDE is it's basically seamless, right? So anything you can do on the command line, you can do in the IDE. So effectively what you do is you launch your IDE from the environment from which the Flutter workspace was set. So the command back here, say for instance in the case of source Flutter workspace setup environment.sh, that sets your bash set, process environment. And then anytime after that, you can just do cd My Amazing App and then type code space dot, and that gives you Visual Studio Code with awareness as to your Flutter SDK and location and environment. I'll walk through a GTK Gallery scenario, and the point of this is to contrast the Flutter-auto Gallery walkthrough. So we're going to compare and contrast starting with the GTK. So first we cd into the gallery folder, we Flutter run -d Linux. If there are no other custom devices installed and you leave out the -D Linux, it will default to the available platform that's present. And typically, if you don't have any custom devices installed, it will default to the host machine type. So what this does, this generates an executable and a build folder. And looking at the build folder, it creates a bundle. So within the build folder, we can see there is at the root the bundle right here, and then we have data, and then Flutter assets. So Flutter assets is the output of Flutter build bundle, and that generates the Flutter assets folder. So that's one step in the build. And so all these items here, I left out all the other details for brevity's sake. And then there's an ICU DTL.dat, and the executable itself, Flutter Gallery, and then lib. So Flutter Gallery, if you do an LDD on that, you'll see the RPath of the lib Flutter Linux GTK as well as the lib URL launcher Linux plugin. So when this executes, the relative RPath allows it to load the SO files. The Flutter assets folder, this is a copy of the build subfolder Flutter assets, as I mentioned, and it's generated using Flutter build bundle. ICU DTL, this is a Flutter engine build artifact. In case of host, x86-64 or Arch64, this is downloaded from Google Cloud Storage. And the Flutter engine depends on the ICU library. And this has more information on what that file contains, the ICU data. So Flutter Gallery is the executable generated by Flutter Tooling. It links with these two shared modules. It contains the base application code which creates the main loop, makes GTK calls, talks to platform channel, etc. It's sort of like the bare minimum code set to create a logical Flutter view. So libflutter linux gtk.so, this links with libgtk30, libgdk30, etc. There are many runtime dependencies on this. It is effectively the kitchen sink for Linux desktop Flutter usage. It's downloaded from the Google Cloud Storage. When you type, Flutter run-d Linux, it looks for, well, first off, when you run Flutter Doctor, it checks the system to determine if you have the runtime dependencies installed correctly, and it will show red if it's not installed correctly. So one of the functions of Workspace Automation is it sets up all the prerequisites for those runtime dependencies, so you're assured that it will not fail when you type Flutter run-d Linux. So this artifact is downloaded as needed. It is an artifact of Flutter engine build, and MetaFlutter, the Flutter engine recipe, can optionally build this using the following package config variable value. It's called desktop-embeddings, and that will also get installed side by side with the libflutter engine.so. So it's an optional step. Once cross-compilation with CMake is implemented in the SDK, then this will probably be used more frequently. LibURL launcher Linux plugin. In the case of Gallery, this is a shared module built by the Flutter Tooling, and it gets referenced from the top-level pubspec.yaml. by the name of URL launcher. And it refers to this package. And the top level CMake references this CMake file. So effectively it's doing add subdirectory, CMake lists, or it's doing an include. Don't recall off the top of my head. So what this shows up as a unique CMake target, and this shared library is built in the same compilation pass as Flutter Gallery executable is. MetaFlutter does not support building CMake based plugins at this time. So to invoke the Flutter Gallery application, either execute flutter run-d Linux, so that will compile it, link it, and then run it. Or if it's already ran and you want to run it separately, you can execute it straight out of the bundle folder. And that is due to the RPath settings allow that. You don't have to export LD library path or anything. So in the case of building the gallery app for Flutter-auto, we cd into gallery, we flutter run-d desktop auto, and this will generate a bundle folder. So depending on the custom devices installed, it could be desktop auto, it could be QEMU master, AGO QEMU master, or whatever the names that are available in your config, and it will generate the bundle folder. And the way it looks here, it looks very similar. Notice the missing component is a runtime executable, but otherwise the data structure, the directory structure is identical, and that's what I've patterned this from, is the GTK ephemeral build. So Flutter-auto AGL is it's an executable generated using IDE home screen repo. Its hard links include the graphics backend. It contains base application code which creates a main loop, makes backend calls, talks to platform channel. Sounds familiar. It dynamically loads libraries as needed. So for example, libflutterengine.so, that is equivalent to libflutter Linux GTK, but with a much lighter weight version. And so dynamically, I'm loading this at runtime opposed to hard linking against it. And this has a number of benefits. We can easily switch versions of the SDK and pull down or build the Flutter engine embedder as needed, so you can quickly switch between versions. It's pretty handy. And invoking the application, we either can run flutter run-d desktop auto, and that will create the bundle folder and execute Flutter-auto, and you will see the gallery on your screen. If you want to manually do this after the fact, or if you want to execute it on the device and it's not currently running, you can do this command. Now, moving on to Workspace Automation. It's a script that uses JSON config files. It creates a reproducible development environment. So it's handy for new members on the team, or if you haven't worked on something in a while and you want to recreate the environment and get to a known state. It's a great tool for that. And it clones selected repos as defined in the repos.json file. It clones the Flutter SDK based on the global config value of the Flutter version. And by default, it will always use Flutter runtime equals debug engine. And that is due to custom device support only supports debug. So if you want to set up a manual profile or release build, you have to do that manually. Workspace Automation has agnostic support for QEMU, Docker, remote, host, generic, fast boot flashing, mass ROM flashing. So depending how the artifact section and the runtime section is defined or tagged with fast boot, what you can do is you can set up your build artifacts as part of your config for a given device. When you execute the Workspace Automation the first time around, it will collect all the artifacts and cache them into a folder. And then after the fact, without network connectivity, you can run fastboot on a target. So this is handy if you need to share it with third-party vendors. You want to give them an image and then also allow them a method or methodology to flash. So fastboot is one, mass ROM is another. So in the case of mass ROM support, there's thinking of Rockchip, Qualcomm, you name it, where there's a built-in mass ROM that is actually your bootloader when everything else fails. So it prevents the device from being bricked. Workspace Automation also generates setup_env.sh, which is used to start the Flutter dev environment. And it used to be in MetaFlutter under the tools folder, and I've since relocated that to MetaFlutter in its own repository. AGL setup. Now, running the script requires sudo and will modify your system packages. So if that is a surprise to you, or if you don't want to do that, then you're welcome to manually go through all the steps. There's a lot of them, but you're more than welcome to do that. So this sets up Workspace to an own state. You create your AGL workspace, you navigate into Meta AGL Flutter WAC tools, and execute Flutter workspace.py. This is a Python 3 script, and running the Meta AGL Flutter config, it will add the following custom devices to the active Flutter workspace: AGL QEMU Master, AGL QEMU Octopus, and Desktop Auto. So if and only if the QEMU session with AGL QEMU Master is active will it show that it's available and present. So it uses the ping command as discussed in the custom devices section. If it finds that port is not available, then it will not show that that is an option. Same thing for QEMU Octopus. In the case of Desktop Auto, the ping looks to see what kind of session you're running. If you're not running a Wayland session, then Desktop Auto will not be available. Workspace Automation Customization, designed to support custom configurations. Data is separated from a common implementation. Not all organizations use the same development workflows. So some may use Wayland session-based, direct on a desktop. Some may use Docker Compose-based on a desktop via Docker containers. Some may actually physically only have a device on target device, cross-compiling native code and pushing sort of the manual method. So all three of those are expected to exist, and no surprises. Not all organizations use the same target hardware. So you could have multiple definitions, and you can have a configuration unique to a organization. So maybe one only has access to reference design hardware, one has access to production, one has only simulated because they didn't have the hardware budget. Or maybe there's so many engineers that it's not practical that everyone gets a reference design or a production hardware. So that's a scenario. Moving on to testing options. So Flutter Analyze effectively runs before when you run Flutter build bundle, but Analyze can do a pre-stage, and you can do some fixing. It's kind of a handy tool, especially when you are looking at making jumps in Flutter SDK versions, and it'll give you some ideas of what you need to change. Another testing option is running Headless using the GTK. This enables running a Flutter application in a CI pipeline, so no GPU. So this could be pretty handy in a number of cases. Host testing using integration_test, which is a package that was on pub/spec YAML and it moved into the Flutter SDK. So the pattern looks like this. We would set up our environment, you cd into My Amazing App, and then you execute your the Flutter drive command. I did hit an issue with this. This is something I looked at recently, and the Flutter team is considering this unsupported use of the tool, but we will make this work. All right, and resources. So the usual suspects: IDE home screen, Flutter, Workspace Automation, Flutter SDK, and the Flutter engine. So, and that wraps it up for my session. So please, thank you for attending and for your attention, and please, any questions?
A question? All right.
Hi, I'm Panasonic Automotive Systems. I'm Atsuya. Thank you for great presentation. I have one question. You explained environmental variable GTK backend for Wayland. So I'm interested in changing backend in Agile. Can you set DRM backend in Agile for Flutter?
DRM backend or AGL and Flutter. If there's two options for DRM, right? One is implementing a DRM only host. Another is Wayland DRM using a lease DRM protocol. If that's something you're interested in having supported, I will look into implementing that. Okay. Effectively, the only difference in that case is the backend. And so the way I've implemented IDE home screen / Flutter-auto is to add in multiple backends as needed. So one scenario is the lease DRM. There actually is a cookie crumb in one of the CMake files that indicates that. And another is actually implementing straight DRM as well.
Okay, I think so. Thank you very much.
We're running a little short on time. Does anyone else have any questions? All right. Thanks, Joel.
Yeah, thank you.